First off, know that these compound interest problems are really good things for especially those of you that are almost done with high school, right? This being your last semester, you're about to transition to a world where you're able to take out loans, open up credit cards, make your own investments, and all of those things are represented by exponential functions. Okay, the way you accumulate interest is represented by an exponential function, both whether that be a loan or a credit card, or even if you're gaining money in different investment accounts, it's all related to this. So I've always liked this unit because it's relevant to kind of where you are in your young lives, okay, where you're getting close to dealing and thinking about all these things very soon. So it says you decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first account pays 7% per year, compounded monthly. That is a really important word here. And then the second account pays 6.85% per year, compounded continuously. Which is the better investment? Now, we need to decide which equation are we going to use and why. Well, the words matter here. So when it says compounded monthly, we're going to use the equation that has the compounding periods. Periods being that it could be really any of these things, and it could be compounded in a number of different ways. Okay, so in this case, when it's compounded monthly, we're going to use this top equation. So some things about that top equation, let's just write down kind of the information here. So 7%, we have $8,000 to invest over the course of 6 years. And it's happening monthly. So our equation, A equals P times 1 plus R divided by N to the power of, that's N times T. And this is what you should have had in your notes from yesterday. So I want to talk about what each of these variables represents. The P, that it stands for the principal. That's essentially your starting amount. So in this case, the P is going to be 8,000. All of these equations have 1, and that 1 is essentially representing 100%. When you think about adding percentage onto an account or into an investment, you're keeping your initial 100%, and we're just adding on the additional percent that we're gaining. So that 1 in this equation essentially represents 100% of our initial investment, keeping that amount as we accumulate interest. The R, that is your percent, but we need to convert that to a decimal, which we'll do in a second. The N is how often it's compounded. So in this case, N is going to be 12, right? If it's compounded monthly, that means it's happening 12 times. So here's what this equation is telling us. Essentially, we're taking our percent and dividing it by how often we compound it. So that 7% annual interest is getting broken up into 12 smaller chunks. And so that percent each month is less than 7%. In fact, it's 7% divided by 12. We're also going to gain this interest over the course of 6 years each time we compound the interest. So that's every month for 6 years. That's why the exponent is that N value, in this case 12, times the number of years, which in this case is 6. So let's go ahead and just add in all these values. Principal being 8,000. The 1 representing the 100% that we're hanging on to. R, well, 7% is 0.07. So we're going to convert that to a decimal. And then or divided by how often we compound it. So like I said, that 7% is getting divided into 12 smaller percentages. And all of this gets applied 12 times 6 times. Here, every month over the course of 6 years. And from here, it's basically just a calculator problem. Now, when you go to the calculator, you're going to need to add an extra set of parentheses around the R divided by N. Some of you might even be a good idea to add an extra set of parentheses into the exponent. Okay, that's most of the errors that I see here are more calculator errors as opposed to you not knowing how to plug things or set up the equation. So I'm going to type it in all in one go. So 8,000 and then 1 plus parenthesis 0.07 divided by 12 and then to the power of 12 times 6. Because this calculator just automatically puts me in the exponent, I don't need parentheses around that exponent, but never hurts. And with money, we want to think about rounding. Okay, where is an appropriate place for us to round? Well, to the second decimal place, right? When we think about money, we have a hundredth of a dollar and a tenth of a dollar. So that 0.84 is what we're going to round it to. So this value is 12,160.84. Right, so that's how much we're gaining over 6 years in that first account. The second account, the key word in the second account is that continuously. If we see the word continuously, we're going to use the second equation that you all wrote down yesterday. This one is usually described as the PERT equation. That's how I remember how to set it up. So it's P, the base is E, that same E, the natural base we talked about yesterday, to the power of R times T. So again, let's just write down the things we're using here. The 6.85%. It's still $8,000 being invested. It's happening over the course of 6 years, and this time it's continuously. Continuously telling us which equation to use. So we're going to go A equals the principal or initial investment of $8,000. E is our base, that's that natural number. And to the power of, we need to convert the percent to a decimal, so 0.0685. And then times the number of years, 6. Okay, so if you look at the PERT equation, T in time will always end up being years. That, for whatever reason, that's how the continuously equation works. That percent will always be given in a year. We don't need to do any conversions there. And now we just got to plug this in. Once again, parentheses are going to be important here. Definitely want to put parentheses around the 8,000. That should be plenty of parentheses for this to work out the way we need it to. So I'm going to go open parentheses 8,000, and then E. To get the E button, I mentioned this quickly yesterday. I don't think the notes are very clear about it. Most calculators are going to have a button that says ln. That's the natural log. We're going to talk about logs here in just a few minutes. But that's a log with a base of E. And so to get E and any exponent, we're going to type second ln and then e to the power of 0.0685 times 6. We end up getting 12,066.60 is that amount. So before we answer the question, this is why investments and gaining interest is so valuable. By putting $8,000 into this specific account and letting it sit for 6 years, both accounts are making over $4,000 for doing nothing, okay? Nothing at all. And that's, again, why so many people invest their money and find ways to just get income from that. Know that this also can hurt you in a negative way. When you take out a student loan, let's say you take out a student loan for $8,000, you are going to have to pay interest on that. Meaning, if you take out a loan for $8,000 and have to pay it off over 6 years, you're paying an additional $4,000 on that loan. So that's why interest rates are so important. I don't know how much you all follow kind of the economy and how interest rates have changed over the past few years. They've been all over the place. They hit a record low back kind of right after the pandemic kind of ended. And now they're raising to really high rates again. Okay, all of that is really important to think about as you start to take out loans for college, for cars, eventually to buy a house. You want to be thinking about those things. All right. So now to answer the question, which account is better? Definitely the first account, because we are gaining more value over the course of 6 years. And I bet if we were to run this like 20 years even further, this account is going to be significantly higher than the first account there. Okay, Any questions about these compound interest problems? Is it sparking a memory for most of you from last year? It's literally the last thing you do in Algebra 2 for most classes. Okay, we're going to actually continue with notes. Based on kind of how yesterday was, we got a little bit behind, so we're just going to continue these notes. Hopefully we get through this fairly quick. And so a few things I do want to go over before we get going. Nevi, do you mind closing that door for me, please? Okay, so this is going to be our introduction to logs, something that you probably have seen, definitely have seen before, because it directly relates to an exponential. And in fact, that's what I want to start out with. A logarithm is the inverse of an exponential. And that's something I would add into your notes. And so the way that we want to think about logarithms is we want to think about them as exponentials. We're fairly familiar with exponentials and how exponents work. We're not familiar with logarithms. But if we think about them as a different form of an exponential, it kind of gives us a place to start to think about. Okay, so they're inverses, they behave in a similar pattern to exponential functions. Now, we've done a lot of stuff with inverses already. And so here I have a lot of information for what we've already talked about with inverses. I don't know that I want to dive into that, but these are important things and things that we have kind of touched on with inverses in the past. But for the sake of time, we'll kind of skip over that. Might be a good thing to kind of review as you look through these notes. So here's one of the main things we did with inverses. I gave you an equation. I said, find the inverse of that equation. And so how we do that is we have f of x equals b to the power of x. We change f of x to y. Then we switch where x and y were located in the equation. That was us finding the inverse. We then work on getting y by itself. Well, if you try to go from this step to this step, you're like, how do I undo taking something to the power of y, and where does that base go? Hence why we get the log. And why logs can be so confusing, because it feels like a word added into the equation. Okay, so that's going to be the first thing we work on. How do we go from an exponential to its corresponding log statement? And here's the direct relation. In log form, it'll look like y equals log base b of x. Notice where the exponent is. In logarithms, what the log is equal to is the exponent for its exponential form. The base of the log is still the base of the exponential. And the corresponding statement in exponential form is b to the power of y equals x. And we can convert between both of these. And that is, to me, the key to logarithms. If you can take a log and convert it to an exponential, and an exponential convert it to a log, to me, this unit is not hard. Okay, a lot of students have felt like this is one of the harder units in Algebra 2, but it's a lot of times because they don't get this down, and it's not a hard thing. So here's how I remember how to convert from one form to the other. So let's just rewrite these, where if I had b to the power of y equals x, and I want to convert that to a log, what I remember is, first I need to bring in that log, which, think about it as an operation. Think about it as adding, subtracting, multiplying, dividing, but closely related to exponentials. So I start with log. The base of my exponential is the base of the log. Okay, that's one thing that stays consistent. And the last thing that I think about are the other two terms change locations. So instead of it being log base b of y, now it's log base b of x, and it equals y. And there's an easy way to check this. If I hide the word log, doesn't that look like b to the power of x equals y, where the base has stayed the same and I just change where x and y are? Okay, so it's an easy check. It's an easy conversion. But again, really, really important. And if you get that down, to me, this unit is Not all that bad. So just real quick, we're going to convert these log statements to their corresponding exponentials. I'll do A, and then have you all do B and C. So I have 2 equals log base 5 of x. So as an exponential, I'm going to start with the base, stays the same, and I'm going to change the location of the other 2 terms. So 5 to the power of x equals 2. I did not change it, did I? That's not right. Let's try this again. 5 to the power of 2 equals x. We can actually solve this, and that x is 25. Now, before I have you do B and C, I want to talk about what we just did there. We basically found that log base 5 of 25 equals 2. And again, how I would see that, if I saw log base 5 of 25 and I needed to evaluate that, in my head I'm thinking 5 to the power of what is 25? That would be 5 squared is 25. Again, think as exponentials, or think of logs as exponentials. This is what we were looking for there. All this up, this was just extra. Let me kind of explain what we're doing there. All right, real quick, why don't you convert B and C into its exponential form? Okay, here are your corresponding exponentials. B to the power of 3 is 64. We could probably find that value of B isn't 4 cubed 64. I think it is. Yeah. Okay, so that'd mean that B is 4. Not what we're doing in this exercise, but something that we want to think about just to get more familiar with logs. And then for C, it's 3 to the power of y equals 7. Okay, so again, keep the base the same, change the position of the other 2 terms. Questions here? Okay. So now we're just going to do the opposite. And we're going to take each equation and convert it into its log form. Again, the process is the exact same. Where I'm going to start with log. I'm going to keep the base the same, so log base 12. And I change the position of the other 2 terms. So it's log base 12 of x equals 2. Why don't you all take 1 minute and convert B and C? Okay. Part B is log base B of 8 equals 3. And then part C, log base E of 9 equals y. Now, one thing about part C here, when we have a log that is base E, that is equal to the natural log, okay? That includes the natural base, hence the name the natural log. It is represented by ln. So you might see log base E of 9 written as the natural log, or ln of 9, and it equals y. Okay, those are the same thing. And we're gonna see that here in a second. I'm gonna actually remind us about it again on Monday. Okay, so your math Excel is going to consist of questions like that, converting between exponential and log form. And the last one is going to be you evaluating logs. And the goal of this is to be able to do it without the use of a calculator. Okay, so I'm going to show us a few different ways of how we can approach these and find the values of logs. Again, think about them as exponentials. So here's what we want to think about when we see like log base 2 of 16. We're basically asking ourselves 2 to the power of what is 16? Okay, that is the value of log base 2 of 16. Whatever the exponent is, so 2 to the power of something is 16. Well, in this case, 2 to the power of, 4? Is 16, meaning log base 2 of 16 is 4. So when we see logs, again, you're essentially making that conversion to an exponential. the base to the power of what equals what we're taking the log of. So in part B, we're thinking 7 to the power of what is 1 over 49. Now, another way to do this is set these equal to x. And when you set it equal to x, you can then do that conversion to an exponential, where I keep the base the same, change the location of the other two terms, so 7 to the power of x equals 1 over 49. And this is where we have to remember some of our exponent rules. I can rewrite 1 over 49 as 7 squared. And if I want that base to move from the denominator into the numerator, I make the exponent negative, or I change the sign. So it's 7 to the power of negative 2. So for these to be equal, x needs to equal negative 2. So in other words, what we just decided is 7 to the power of negative 2 is 1/49, meaning that log base 7 of 1/49 equals negative 2. Okay, real quick, why don't you all find C and D? Those ones are a little bit trickier. Let's see if you can come up with a good educated guess for what those logs equal. Okay, what I've done is I made the switch from a log to an exponential. You don't need to do that as long as you're in the habit of saying, okay, 25 to the power of what is 5. That's essentially what the conversion is getting us to anyways. Now, this requires you to remember some specific rules about exponents. And so on the side, let's just jot what I'm referring to down, in that if we have the square root of x, that's equal to x to the 1/2 power. If we have the cube root of x, that's equal to x to the 1/3 power. So fractional exponents are really us taking roots. Whatever the denominator is the root that we're taking. So when I look at this, I'm like, oh, I know the square root of 25 is 5, meaning that x needs to equal 1/2. 25 to the power of 1/2 is us taking the square root of 25, which is 5. Over here, one way that I can see this a little bit clearer is rewrite this as 2 to the power of 1/5. And so I'm like, oh, the bases are the same. For the exponents to be the same, I need x to equal 1/5. Okay, so in this unit, some of your exponent rules are going to pop back up. Okay, the last thing I have are just some like general rules for logs. These are not things that you necessarily need to memorize. If you have them memorized, it makes it some of the evaluating go really quick, but you can always find these properties by converting from log to exponential and vice versa. So there are two specific types of logs that show up fairly frequently. So first, let's jot down that a common log is a log with base 10. If you look on your calculator and find the log button, you're going to notice that it does not have an option for you to change the base. Okay, it is already that common log. And so if you ever see just log of x, that is equal to log base 10 of x. So if there's no base, it is assumed to be base 10. And then below, this is the natural log. I kind of talked about this. This is a log with base e. And so if we ever see log base e of x, you're mostly going to see that rewritten as just ln, which stands for the natural log of x. All right, so the other things in these notes here are it's repeating the same thing. Okay, the rules that apply to general logs, so logs with any base, apply to common logs, apply to natural logs. So what I would do is maybe just write down this one column and then say that these apply to all logs. Right, and then that is the last thing for today. So after you have that written down, it'd be a good time for you to open up Math Excel. Want to make sure you can all get logged into Math Excel. The other thing you can work on is the graphing exponentials worksheet if you did not turn that into me yesterday or this morning. I will leave these up here, and then I'll put the slide of your homework here in a second. And the rest of the period is your time to work.